So, another technique that you might have in algebraic manipulation is completing the square. And this is a cool technique you can use when there are quadratics in the denominator. So you might have sort of an integral where there's a quadratic like that with like a function on top, and you might have the quadratic within a square root. So the trick is you kind of want to use the adding and subtracting algebraic manipulation trick to sort of get the top to resemble the bottom, and afterwards split the fraction like what we did earlier, and then see if you can get the reverse chain rule. Manipulate it so that you can try to do the reverse chain rule, and then for the second one you want to complete the square and then use a standard integral for that leads to an inverse trig result. So that's kind of confusing when it's written out like that. So let's just look at an example, just sort of see how this is applied. So yeah, this works if so you can see if you've got a squared plus bx plus c, the derivative of that is 2a plus b. So you want to manipulate it so that the top has a 2ax plus b, because that's the derivative of ax squared plus bx plus c, and manipulate it so that you can apply the reverse chain rule, and then you can complete the square for the second fraction. And that's only if there's an x term in the top already. So, and this also is only when the bottom is irreducible, meaning it can't be factorized. So let's take a look at an example. So let's say we are asked to integrate x over root 6x minus x squared with respect to x. So notice how here in this fraction we have a square root. We've got a square root in the bottom, and we also have an x term in the top. So let's try to manipulate it so that the top has the derivative of the bottom. So within this, so there's a function here, but within the function is another function, which is 6x minus x squared. The derivative of 6x minus x squared is 6 minus 2x. So I'm going to have to algebraically manipulate it so the top resembles the derivative so that we can apply the reverse chain rule. So what I'm going to do is I'm going to multiply by negative 2, first of all. But I can't just multiply by 2 without balancing out the fact I did that by dividing by negative 2. Like that. And now I want to get a 6. So I'm going to add a 6, but I'm going to also subtract a 6 as well at the same time. So I can not change the question. So this all simplifies just to what we had originally with x over root 6x minus x squared. The reason why I did that is, so now I can split this off. So this will become 6 minus 2x over root 6x minus x squared minus 6 over root 6x minus x squared, like that. Now, I can split the integral now. So let's just, on the left-hand side, not the left-hand side, on the left here, this will be the same thing as negative half integral of, this is 6 minus 2x. Notice this is already the derivative of the thing inside, so we can directly apply the reverse chain rule on that. So we've got 6 minus 2x times 6x minus x squared to the power of negative half. So we can directly integrate that. Here, I can say negative half times negative 6 will be plus 3 over 1 over root 6x minus x squared, like that. Like so. So basically, I just split the integral into two integrals. So we've got this integral here, and then we got the plus 3 over 1 over root 6x minus x squared. So this one we can directly integrate now using the reverse chain rule. So we've got a negative half out the front, and this will be 6x minus x squared raised to the power by 1 divided by the new power. But then over here, we see we got a 6x minus x squared. So what I'm going to do is I'm going to try completing the square. So this will be if I, so we got, this is the same thing as, if I add, so this is minus x squared minus 6x. If I factorized out that, I would need a plus 9 within that bracket in order to complete the square here. But because minus 9, if I did a minus 9, I also need to add a 9 as well in order to balance out the fact. So that I when this expands, it will become a minus 9. So I can't just pull out a 9 out of nowhere. I need to also balance out the fact that I did that. So you can see, yeah, if you want to double check, you can expand this and you'll see it will all simplify to 6x minus x squared. So remember the way we complete the square, we look at this, we halve it, then we square it to tell you what number you need to add in order to complete the square. So yeah, when that expands, will be 6x minus x squared. So now this thing is going to be negative root 6x minus x squared. And this will be plus 3 times the integral of 1 over 9 minus x minus 3 squared. And the reason why we completed a square now is you can see this is a standard form that we know, that we learned in extension 1, because we know it will lead to inverse sine. So therefore, our final answer is going to be negative root 6x minus x squared plus 3 times inverse sine x minus 3 over 3 plus c. And that is our final integral for what we get when we integrate x over root 6x minus x squared with respect to x. And we can see, yeah, that's exactly what we got here from the working. So it will be minus root 6 x minus x squared plus 3 inverse sine x minus 3 over 3 plus c. Okay, cool. So yeah, you can see the difference between extension 2 integration and extension 1 or advanced integration. It is a bit more complicated, you can say, with sort of the algebraic tricks you sort of need to know, and also a good working knowledge of your standard results that you have. So let's try this question now. Let's say we are asked to integrate x plus 1 over x squared plus 4x plus 13 with respect to x. So again, the same sort of guiding principles. We want to, first of all, notice that this thing in the bottom is irreducible. You can't really factorize that. So last time we had a square root, so it didn't matter if you could factorize it or not. But here we don't have a square root, so you want to pay attention and make sure this isn't irreducible. You want to make sure it's irreducible before applying this technique. Because if it is reducible, if it is factorizable, instead you'll have to use partial fractions. But here it's irreducible, so we can try using this technique. So the derivative of x squared plus 4x is going to be 2x plus 4. So we kind of want a 2x plus 4 in the numerator. So let's do some algebraic manipulation to sort of see if we can get the derivative on the top. So I can multiply everything by 2. So that will give me 2x plus 2 over x squared plus 4x plus 13. But then if I do multiply by 2, I need to also balance out the fact that I multiply by 2 by dividing by 2. But now I want to get a plus 4. So what I can do is I can say that 2 is the same thing as plus 4 minus 2. Yeah, so I basically converted 2 into plus 4 minus 2. So we can have a 2x plus 4. Yeah, so I rewrote the 2 as plus 4 minus 2, so we can have a plus 4 there. So now that we have this, we can split the fraction. So this is the same thing as half 2x plus 4 over x squared plus 4x plus 13 minus 2 over x squared plus 4x plus 13. Like so. And we can, I suppose, do what we did last time and just split it into 2 separate integrals. So we got half 2x plus 4 over x squared plus 4x plus 13. And here we can say this is minus integral of 1 over x squared plus 4x plus 14 because the half and the 2 cancels out. And don't forget your dx here. Okay, so this one is a direct application of the reverse chain rule. Notice there's a function here in the denominator. The derivative of that is 2x plus 4, which we manipulated to get at the top. So this is simply going to be half ln absolute value of x squared plus 4x plus 13, because it's an application of the form where you got f dash of x over f of x, where it's 1 over f of x, but the derivative is already being multiplied on the outside. Okay, so we got that. Here, we can do what we did last time. In order to simplify this, we can try to complete the square. So this is the integral of x squared plus 4x. In order to get, to complete the square, divide 4 by 2, I get 2, square 2, the square of 2 is just 4. So I want a 4. But in order to get a 4, I can just split the 13 as a 9. I can get a 9 out. So 13, I split it in the sum of 9 and 4. So I get the 4 I want here. So now this is going to be when I complete the square, I get 1 over 9 plus x plus 2 squared. Like that. And remember, with the inverse tan form, it's going to be a over a squared plus x squared. So I want the a here. So a in this case is going to be 3. So what I'm going to do is I'm going to have the 3 up here, but also divide by 3. So I'm not changing the question. So now my final answer is going to be half ln absolute value of x squared plus 4x plus 13 minus a third inverse tan x plus 2 over 3 plus c, using our standard results that lead to inverse tan. So you can see, yep, that's what we got here. We got, also what you can say here is you can, you can, actually this thing inside is always going to be positive. So technically the discriminant here is negative, which means that there's no, real solutions. And also it's a concave up, so it's actually going to always be positive. So you can actually remove the absolute values if you want. You can just leave it as round brackets, which is fine. But yeah, it's just the exact same answer here. So yeah, you can see the same principles, just slightly different, because instead of a square root where we got inverse sine, we didn't have a square root, so we got inverse tan instead. But yeah, just got to be careful with your algebraic manipulation and also manipulating it so that you get the standard form where you can apply a standard integral. Okay,